Okay. This time with live stream. Right, if you've made it to your seat, log into Slido. Also, maybe use the 2 minutes before we get started to sign up for CampusWire if you haven't already, and check out that platform a bit. I posted a first post from our side explaining the platform a bit and how we're intending to use it. It's not anything really new from what I told you yesterday. And the link is, of course, also in the announcement on Canvas. I've heard of, well, a sawmill worker's handful of people, 2 or 3 people who have not been assigned some tutorial group. If that's the case for more people, check out with the student office as soon as possible. No tutorials this week, so you can sort it out for next week. But if you haven't been assigned a tutorial, it likely means you haven't properly been registered for the module and might cause other trouble. So get that sorted before the first 2 weeks end, which is when the normal phase for changing modules ends. With regards to the prior knowledge survey that I put out yesterday, 57 people have sent in responses already. So that already gives some indication, but I want to leave it open for a bit longer so you all have a chance to try it. And we'll discuss it a bit next week on the Thursday slot. What one person sent on Slido, they can't hear me well. Is that in the live stream or is that here? If it's in the room, I can try to use the mic. If it's in the live stream, I have to check if the setup, otherwise the tech is fine. Can you all hear me in the back of the room? Is that loud enough? Was that a no? Yes? No? No? I can try to speak a bit more into this one. That should project well. It's a bit of a challenge to keep the same distance while writing and so on. So you'll have to live with that part then. Attendance code. So again, sign up on CampusWire if you haven't. The attendance code, you know how it works. I didn't reset the answers from yesterday. Maybe I can do. Okay, now you have a fresh chance to send the got it. It's a different attendance code for each session. All you need is the code. The Slido question is not so important. All right, then I think we're ready to go. It's on Slido. If you log in with your phone, you should be able to see it still. That one. I also think 4 digits would have been enough. Like how you can't really guess it. But remembering 6 digits, it's early morning. Come on. Right. Any other problems so far? All right. Then welcome back to COMP526. In the rest of Unit 0, still kind of before the actual topics, I want to discuss a few proof techniques. So these are some mathematical preliminaries that we'll use in the background in the following. It's more a bit about framing the language we try to use if we want to be very precise. And I think it's important that you're able to understand such kind of proofs and read them. We won't usually go to all the level of detail that I'll show you today, but I think it's important to know what that level of detail looks like so that you can recognize it and you can reproduce it if you have to, where things need to be extremely precise. And so the goals for this unit is to learn some templates for proofs, how they are structured to follow the logic of the statements. Specifically, the useful tool of mathematical induction, because much in computer science is about discrete mathematics. Induction is a key tool that's often used. And we'll briefly look at the case where computer science often uses formal proofs. That's for proving the correctness of programs. That last part is not the key topic for this module, but I want to give you a glimpse of it either way. I'll start with a little digression that some of you have picked up already on CampusWire. I'll come back to that. And then we'll go through these things, the general proof templates and induction in a bit more detail, and then how to prove programs correct. I want to start by motivating this a little bit. Hold on, I'm on the wrong deck of slides. Let's try again with this year's date. The rest so far wouldn't have been different. I want to motivate a little bit, apart from just me telling you it's important that you are able to read proofs. I want to motivate a little bit why it's useful to make very formal statements about algorithms. And I want to give you a small example of an algorithm that looks innocent and looks correct. And even if you try it, maybe it looks fine, because it has to do with randomness. And randomness is tricky to pin down with tests, because they come out different each time. Right, so a toy problem. You're given an array of numbers, and you want to put them in completely random order. You want to shuffle them. It's a function that most standard libraries already have, so maybe you don't have to implement one. The point is, this is a simple example that fits on a slide to illustrate the point. So how would you do that? Well, you could say I pick a random position for each number, and then I swap. Each position in the array gets swapped to a random other position. And by random, I mean a uniformly distributed random number in that range. So that's all good. Once you've done that, pretty much no element is where it was before, and they're all kind of at a random position. So it looks like a sensible way to do. And then maybe before I dive deeper, I'll ask you a bit about this. I'll swip back to the code in a second. Where is my question? I've opened the question on Slido now, but I'll go back to the code so you can take a quick look at that. So note that you can select several things. So we had something like 130, 140 people on the previous Slido calls. So I would hope to see a similar number for this one. While we're waiting, there's two questions on Slido that I might answer. So the lecture today stops before 1. The slot goes until 1, but we started 10 minutes late, so we should be done by 20 to 1 the latest. And the password for Campus Wire is on the announcement on Canvas. Again, 4 digits. I can't be bothered to remember them. So as you can see, we have various statements got votes. Now, around a third or so have trouble reading the pseudocode. So maybe it's worth going over that part just briefly. So this is a kind of pseudocode that is a little similar to many languages and has similarity to Python, but is I tried to use the syntax that is more unambiguous as opposed to more Pythonic. For example, I use this :equal for assignments because equal always is a bit ambiguous. Is that an equality comparison or is it an assignment? So I'll try to use this for assignment and the double equals for equality comparisons and never the normal equal. So I'll try to make it a little less ambiguous. And then sometimes there's just things like swap the 2 positions in an array where it's just an English language sentence that if you have some programming language, you probably can translate to how that looks in a concrete language. And OK, here I was just lazy. You could, of course, assign a of I to some temporary variable, then assign to a of I, a of r, and then a of r becomes the temporary variable. That's just a shorthand. And this is a function call where I didn't show you how this is implemented, but let's suppose this is part of the programming library that we're using. And indeed, Python has a library for doing that in the random library, and all languages I know have a way to choose a uniformly random number. So let me show what I marked as the, well, correct for me. The second one is, of course, depending on who answers. And sort of same for this one. It's also true. Okay, I mean, so remember, you can change your answer now, and you can make the green bars go all the way to the right. But there's no real point. You don't get extra marks for being correct on those. And it's more interesting to see that a lot of people thought, for example, this answer is correct. Now, if you keep changing the numbers, or more people add it, they kind of skew the picture a bit. But the point of these polls is to give you a feeling what the room thinks, and also give me a feeling of what the room thinks. But if that bar goes up, I'm happy. It can generate all possible orderings of the array. That's true, but all the others are not. In particular, it's not really solving the problem we are trying to solve. I'll just demonstrate you briefly why. If you take an array with just 2 elements and you call this function and analyze how likely is it to go each way. So what I'm showing you here is the probability that the outcome is 1, 2, the same order you put things in, or 2, 1. That's the only 2 possibilities with 2 elements. And they're equally likely. Great, so we're on track. But if you start adding more elements, for 3 elements, there's already 3 permutations that are a bit more likely, and the other 3 are a bit less likely. Now, how did I arrive at those numbers? And that relates to the campus wire question. And I want to give a shout out to the campus wire question. It's great that some people experimented with the code, implemented it, and tested it. It's good for 2 reasons. It means you engage with the material. And the second one, it is nice for me to make the point that randomness is tricky to nail down with tests. Because they implemented the corrected version that I'll show in a second. But if you run the method several times, the outcome is random. And so it's hard to gauge if it's correct or not just from looking at tests. What I did to produce these bars is I basically analyzed the function theoretically and looked at what are all the possible outcomes for the calls to this random method. And this is discrete here, right? It only has n different choices in this case, but you have to do it for every loop iteration. If you go through that and go through all possible options, each has the same probability, but the outcomes are not equally distributed. And things get worse if you go to larger lists. And then I stopped because it spiraled a bit out of control. You have many, many things to try. But I want to point out here, this green bar is the average, or is where uniform should be, 1 over n factorial for n elements. And you see some elements are almost twice as likely, some of the specific orders. So it's not even, it's not just wrong in that it's not perfectly uniform. It seems to get worse with larger inputs. And that's a bit, well, it's a problem if you want it uniform. Now, so don't ever use that code. We discussed that. There's a simple way to fix this, and I'm sure some of you will know this. It's a well-known algorithm. I would call it the Knuth-Fisher-Yates shuffle because all 3 were involved in. It's maybe basic enough to have been reinvented independently a few times. The only change you really need is restrict the range of this random position, and then it works fine. I don't want to go into detail why it works. That's not really my point in this unit. And it's also not about, this lecture is not so much about random generation. And yeah, there's good Wikipedia articles about this algorithm. If you repeat my experiment, then you see it comes out perfectly uniform. To give you a quick intuition, why the previous method cannot possibly have worked is if you just analyze the number of possible things it can do. It had n iterations and drew 1 out of n choices each time. So that's n to the n different things. But the number of permutations is n factorial. And these 2 numbers are not equal. And they are even, they're co-prime. So there's just no way this could have worked. In hindsight, maybe this is obvious, or depending on who looks at it, maybe. But that's a quick way to prove the previous code cannot be correct. Doesn't tell you how to fix it, though. But yeah, in this case, it's already been invented, and so we don't have to worry about it. But what's the point of this? My point is the previous code looks quite reasonable. If you read this in a code review, maybe you'd say, yeah, it looks like a good random shuffle. And it looks very similar to this code. So how can you tell them apart with certainty? And again, who guarantees me that I've done this for up to 5 elements? Maybe something wonky happens with 6, 7, or 8 elements. There's too many options for me to try. At the very latest, so maybe 11 factorial is still doable, but 20 factorial is out of the question. It's just too many different things. So there's no way a test will get you to the right answer. So the only thing that's left is a formal proof or a theoretical analysis of the algorithm that can tell you with certainty this one's going to shuffle correctly, right? And that's why we're stressing this in algorithms so much. Many algorithms look reasonable and are just wrong. It's very, very tricky to find the difference, to see the difference. After this bit of motivation why we want formal statements and formal proofs, I want to give you a few specific examples of what formal statements are and how we can prove them, which often follows their structure. So we'll look at that first. At some level, we'll have to talk about what a proof is. And if you want to be very precise, you need a specific logical system where the proof is formulated in, and then it comes down to a sequence of statements. The proof system gives you axioms. These are things that are undoubtedly true, and where you don't have to prove that they are true. And from those and some inference rules, you have to derive the statement you want to prove. That is what a formal proof is. In many cases, we'll confine ourselves to have a little bit shortcuts in there. So it will often be enough for us to convince a human expert. But the assumption there is that if it's needed, you can always fill the shortcuts in with steps in such a formal system. And only if you do that, you get a bulletproof statement proof. So let's do a few concrete examples for statements and also to make this more concrete. So suppose I have these two statements. Statement A is it rains, and statement B is the street is wet. These are my two primitive statements in this case. And let's suppose, for the sake of this slide, that this is completely unambiguous. So there's no, we're in Britain, so there's often drizzle where it's not clear, is that rain or not? So let's pretend the statement is definitely either true or false. And the same for this one. No debates about a puddle on the side and the rest is dry. Let's pretend it's completely black and white. Then we can take such a statement, we can negate it, not A, so it does not rain. If you formulate it in proper English, not it rains. You can take two statements and put an and between them, which means they both have to be true. You can put an or between them, which means either of the two can be true or both. It's not an exclusive or. A or B could be it rains or the street is wet or both. Just want to be clear about that. Then the more interesting cases are implications and equivalence. If I write A implies B with this arrow, you should read it in English as if they, then B. But really, it's formally equivalent to this. And that's important, an important distinction that I'll come back to, but I have a slide or question for you to try that. So just to plug in, the statement then would be, if it rains, then the street is wet. And equivalence is basically an implication in both directions. A implies B and B implies A. which we often in English abbreviate as A holds true if and only if B holds true. And you'll see me use this abbreviation sometimes just because it's quicker to write. It's not a typo. If with double F stands for if and only if. All right? Good. Wake up time. Wake up time for the phone as well. There we go. I don't want to influence you straight away too much. Okay, that's a fair share of people who have voted. So I'll show you the two bars. And is not equally distributed, but there's a fair amount of people for both answers, or even all three. So resist the temptation to change your vote, take it as the average of the room. And in this case, the statement is true. And let's unpack this a bit. Now, just to be clear, I'm not a flat earther, right? This is not where this is getting at. This statement has two parts. There's the, let me do it more schematic. So there's the if then part, which means we're talking about an implication, right? So it will in the end be a formal statement that has this arrow in the middle. And then we have two parts. The Earth is flat and ships can fall over the rim. Let's give these names again, A and B. So the implication, if we define the statements A and B, then the statement is A implies B. Now that hasn't helped us so much yet. But remember what we said, an implication formally, if you have to check it in detail, you should replace it with not A or B. So we can also write this as not A or B. Okay, I haven't invented a symbol for this is the same. Sometimes people use the equivalent symbol and equal with three things for saying the two formulas are equivalent. But if you unpack that again into English, it means an or statement, ships can fall over its rim, or the Earth is not flat. One of those is true, that's fine, and that's good enough. And let's suppose the Earth is not flat, and then not A is true. That means the whole statement is true. In particular, my point here is to hammer in that statement. If you have an implication and the premise, the A statement in the if part is false, the whole thing is true no matter what garbage you claim in the rest. Okay? That's just how it's defined, and this is useful for implications. It makes sense to define it that way, but it's often something people find a bit unintuitive when you first see it. So the first type of rule template that we'll look at is for implications. The others, if you have to prove an and statement or an or statement, it's usually quite clear what to do. If you have an and statement, you have to prove A and B separately, one after the other. If you prove or, then you have to work your way through that the two are somehow, one of them is true. But implications are a bit more interesting. And there's different ways to approach them. You can go for a direct proof, which just means you try to go with all your axioms, but you add A, and then you try to derive B from that. This is what you can always try, but often this is this is not as easy to do. Sometimes it's useful to flip things around and do an indirect proof, or also called proof by contraposition. That follows again from the logical replacement. So remember, A implies B was the same as not A or B. Now, if I double negate A, I can rewrite this as not B or not A. And then it again becomes an implication, namely the not B implies not A. Right? I'm using the same recipe here, but with negations. So those two statements are the same. A implies B or not B implies not A. And sometimes it's easier to go the other way around. That's by contraposition. A close relative is proof by contradiction. That's where you assume the statement is true, and you try to derive something contradictory from it. So you assume that A and not B are both true. Remember, this is that's kind of the negation of that. And you try to arrive at a contradiction, and we'll see some examples of this in the class later. And then another interesting template I wanted to list is if the implication has a specific form. Sometimes you can split cases by adding another thing. So if you're trying to prove A implies B, you can add another condition C and check if adding that to A helps. But then you also have to add the negation of C. You have to prove it for both cases, but it can still be easier to split them up because you have more to work with. And we'll see lots of examples of that in the module. And the important bit is that it's exhaustive. You have to do both cases, C and not C. And of course, you can have more than two. Can add more than one statement. Let's see how far you already have seen this. So here's a slightly longer question. I'll have to give you a bit for that. Right, while you were thinking, I spelled out the proof a bit more, how you may do this in some intro math class. Just to, I don't know if you have to go in detail. It's probably clear. What does it mean that n is an odd number? It means there's another number which is also a natural number, an integer, so that n is 2 times k plus 1. It's not divisible by 2. And then using that, you can calculate what n squared is. And you find, again, it has the pattern of an odd number, namely 2 times an integer plus 1. And so n squared is odd as well. So not a hard proof, but the question that we're getting at here is, what kind of proof template did we use? And most people got this right. Yeah, 130, 140 was where we've been before. Okay, a few more people joined late. That's fine. Well, again, don't vote for the right answer now. That's kind of, yeah, or do if you please, but it's not gonna help anyone much. So this is an example of an indirect proof. Why? Well, the original statement was, again, an if-then thing. We have two statements, A and B. And then we tried to prove A implies B. But what we actually did is we show that if n is odd, then n squared is odd. And that is not B, that is not A. With a slight twist that instead of saying not even, I replaced that with odd in this case. I hope that wasn't a trick question, but we negated the statement. In this case, there's just these two options. Goodie. All right, so far so basic, right? If you have to prove a statement of this if and only if form, you actually already know what to do because it's two implications ANDed together, so you just prove the two implications separately. And almost always that's the most convenient way to go about it. It's maybe not the shortest proof, but it's the easiest route. Then sometimes we have statements that include sets. Sets are the ubiquitous data type in math, and so formal statements about algorithms are also formulated in set theoretic terms. A typical statement for sets could be that some set R is a subset of another set S. Again, subset in this sense means R and S can also be the same. What that means is, again, you're just proving an implication, namely, if an arbitrary element X is in R, then it is also in S. If you want to prove that two sets are equal, that's an inclusion in both directions. Two sets are equal if S is a subset of R and R is a subset of S, then R and S are the same set. So again, everything kind of boils down to proving implications. In the next section, I want to briefly talk about mathematical induction and about statements that have a free variable that already cropped up in the set example. These are the most interesting kinds of statements, and we will usually use those for algorithms because we want to make a statement for all possible inputs. So we can have statements that have a parameter or a variable, and we'll write these as in this notation of a function a of x. An example you could think of is x is an even number. Now I can talk about a of 6 being true or a of 5 being false and so on. You can put in any number. If you have such a statement, you can wrap it with a quantifier that tells you something about what this x should be. The point is, a of x itself doesn't have a truth value. It depends on x. So you can only say whether it's true or false once you tell me what x is. But another option is to say, is there any x so that a of x is true? And usually we want to be clear about what universe x is coming from. So we often specify a set. But this is implicit here. So the set is kind of known. So this symbol exists means there's some x so that a of x is true. In our case with even numbers, of course there are even numbers, so not a very interesting statement. The other version of that, this flipped around a, stands for all. And that means it has to be true for every x in a certain universe. And if we pick as the universe the natural numbers and our statement a of x is an even number, then of course for all x, a of x is not true because there are non-even numbers, odd numbers. Again, you can, if you want, just deal with one of the two. You can write, or the other way around. So one of the two is enough. And what makes these interesting is you can nest them. And this is the part that I definitely want you to be able to read, even though that specific example is not so relevant for us. But yeah, this may be the most likely you've seen. So any kind of analysis class would talk about limits. And the usual way these days to formalize a limit is this epsilon delta criterion, where you say, if you have a function f, what does it mean for f to approach a limit value a as x goes to some value xi? That means for every tolerance epsilon you pick, there's a distance delta, so that if your x is close enough to xi, namely closer than delta, then the function value is within the tolerance of the limit value. Okay? But the important point here are the two quantifiers. You can't flip them around. It's important that they have this order. For every epsilon, there is a delta that may depend on the epsilon. If you were to flip this around, it's a much weaker statement and wouldn't define a sensible limit. Okay? So we'll occasionally encounter statements like this, or even maybe in disguise, because whenever we talk about an algorithm being correct, we want to make a statement for all inputs. And so we definitely have a quantifier there. And if we talk about running time, we'll often use asymptotic notation, which has nested quantifiers in it. So you'll encounter these, even though they're sometimes hidden under definitions. How can you prove quantified statements? For the existential, it's very simple. If you want to prove exists x so that a of x is true, you find some value, some concrete value, and I use xi here again, where this is true. So these are not too hard. You just find an example. For all statements, a few more options exist. And let's see if you've done this before. So I'll hope to get through this one quickly. It doesn't need any thinking. Yeah. And this question is mostly a testament to the diversity of this group. All of those who have an undergrad degree in computer science will definitely have seen it, but the vaguely remember might be you. That's what I thought. And then there's a smaller group who has never seen it before, because it's something more important in discrete math than in, say, engineering fields. You often don't do induction that much because it's not as useful. Right, let's leave it with that. I mean, it kind of means I'll go too fast for the last root and too slow for the first group. But it seems impossible to do it better than that. So for all statements are like this, just what we just had. One strategy that sometimes works is you say, let x be an arbitrary but fixed value, and then you just show your statement a of x based on that. Sometimes you can do such a direct proof. But if that doesn't work, then induction is a powerful way to prove such a statement if the quantification is over a discrete set. And let's pick the natural numbers here, but there are extensions that make this a bit stronger, which we'll not get into too much. So suppose you have a statement for all natural numbers something is true. Then what you can do by the principle of induction, you prove it for a0. You prove that a0 is satisfied. We call that the basis. And then you show that if you're at some point on the ladder and you have proven an is true, that you can jump to the next step of the ladder and this is in the form of an implication. So for every point on the ladder, for every number n, there's a sequence of steps starting from a0 and then using these implications to arrive at the truth for a of n. Now, at first, if you haven't seen this before, it looks like you're replacing something simple for all x, a of x is true, with something more complicated. In particular, we have another quantified statement here and so on. So it looks like this is not helping you at all. And you'll do a detailed example in the tutorials. Last year, the last bar of the group was much bigger. So I did an example in class, but I think I'll skip this here because 80% might find this not too insightful. But you'll do a detailed example of induction proofs in the tutorials on an example that's simple enough to follow with some recursive definitions. And I want to briefly give you an intuition why induction helps. So the big step here is, instead of having to prove a of x without any other help, what we're proving in the inductive step is based on the statement being true at a certain point. We just have to make it one bigger. And that gives you a lot more power because you can use the truth of that statement. It's kind of pulling yourself out of the swamp at your own bootstraps. It feels sometimes almost like cheating, because inductive proofs sometimes don't give you much insight why a statement is true, but they're a totally valid formal proof that the statement is true. The basic version of induction is what I've shown you. You start with a0, and then you go from the previous step one step further. You can strengthen this argument so that instead of just the statement for n, you can use all previous statements and derive from that the next step. That's also fine. And as I alluded to earlier, you can use other things than natural numbers in there, but this I'll mostly just list for reference for the computer science grads who have seen that. We won't use that very much. I think it's a good point to take a little break. I usually try to split these long sessions in half. I don't want to leave it for too long, so shall we say 5 minutes? That's just enough maybe to get up quickly and shake your bones a bit. It looks like most people are back. Anyone still outside, or you all found the way back? Okay, I'll let you take a seat. Given that it's a theater, there's way too few gimmicks. There should be a bell for ringing the end of the break or something like that. Maybe I just don't know where it is. All right, guys, let's continue. I want to bring it back after we talked about mostly mathematical topics that are not so directly connected to our main area of algorithms. I want to bring it back to the more computer sciencey part of proofs. And again, the purpose there is on one side showing you some really formal techniques that make such statements or the proofs very rigorous. Although we will not use them in all the full gory details, that's the kind of thinking that you should develop when you think about algorithms and argue why they are correct. So that's part of this last section. In this section, we'll discuss proof techniques or templates for showing the correctness of programs and what that even means in our case. This is a whole area called formal verification, which is really not the focus in this module. But a little glimpse of it is part of every algorithm design. When you design an algorithm for an algorithmic problem, you want to make sure that the algorithm is fast, but it's only useful if it's fast if it's also doing the right thing. And so implicitly, we always want a correctness proof as well, at least informally. In formal verification, the correctness of a program is split into two parts. One is that the program terminates, so at least eventually it halts, it stops running, which is a far cry from being efficient. And we'll spend the rest of this module on efficient algorithms, but for this section, it doesn't matter how long it takes. That's at least part of the game. And then when it stops running, our assumption is all algorithms are essentially boxes that take some input, and then they produce some output. I'm sure you have seen this box many times, but the implicit assumption among this, I mean, there's some computation going on inside of here. These are cogwheels, obviously, not sunny side up. There's some computation happening inside there, and it's supposed to produce an output. Well, it can usually only produce an output when it stops running, or you would have to define what that otherwise means. So the second part is about producing the correct output when it stops. Now we'll restrict it to a specific part of the program here, but it is actually more general than that. So you can use it on different parts of the program to generalize it. The general template, if you want to prove a program terminates, is something like a potential function argument that you may have seen. In this case, I'm assuming we have some recursive procedure, so a function that calls itself. Maybe if we take a step back, why would a program ever not terminate? Well, it only doesn't terminate if it somehow gets into an infinite loop of some sort. And that can either be a while loop, while something is not true, keep going. And if that never is true, then it is stuck in that loop forever. But it can also happen in a recursive function that keeps calling itself and never stops. In a way, these two are equivalent. If you've had some more theoretical computer science modules, you'll maybe even have proven that. You can translate one to the other and back. But these are the two main reasons why a program might never finish: infinite recursion or an infinite loop. And so for the proof here, we'll assume that there's a recursive function, some procedure proc that has a bunch of parameters, and it might call itself at several places in the body. So what we'll do is we'll define, to show that this eventually terminates, we'll define some function that takes the parameters of this procedure and converts them somehow into a number. And how exactly that works doesn't really matter so much. You'll have to pick a concrete example, and you will do in the tutorials next week, on how to make sense of how the parameters turn into a number. Abstractly speaking, the potential is some function that gives you a natural number back for every set of possible parameters for this function, for the procedure. And because it's a natural, so I'll use this n0 as the set of natural numbers 0, 1, 2, and so on. And I'll try to use n without the 0 for the same thing, but starting at 1. If that's important, I might actually write with a subscript greater equal 1 to make it more clear. So this potential is at least 0 by definition. There's no smaller natural number. What we have to prove termination is whenever the function calls itself, the potential of these parameters that it calls itself with is smaller, strictly smaller than the potential of the parameters it was called itself. So in other words, at least the potential drops at least by 1. Again, because it's natural numbers, if it's strictly smaller, it has to be at least 1 smaller. And that's pretty much all for the abstract template. Again, you'll flesh out in an example how this works next week. But that means the procedure has to terminate because it has to start with some finite value, namely the potential of the initial parameters that it's called with. And whenever it calls itself, something strictly goes down. You can only do that a finite number of times in the integers. Then you flat out at 0 and you can't go further. A similar idea works for loops. If you have a while loop, then there will be some parameters, there's some variables. So it's not as explicit as in a function call, but you will still have variables that change their value over time. And so if the while loop eventually terminates, there must be some way to get a potential from the variables that always decreases. So it's kind of, it works in both ways. But the trick is to find the potential function. Depending on how complicated the code is, that's quite a formidable task. Again, I'll refer you to the tutorials for an example. What I'll show you in detail in the rest of today's session is for the second part, how do we prove the correctness of a piece of code? So let's assume we already established it does terminate. What does that even mean for the code to be correct? The way this is almost always formalized in the form of for logic is that you run a program. Maybe it's worth writing that down. You run a program assuming some conditions that are true. So for example, that your input is of a certain form. You don't accept arbitrary bit strings. You want certain structure. For example, you may have a function that takes a number, and the number should be at least 1. I'm making this one up, but that could be a precondition. Then you run your code. So this could be conditions on the variables, on the input. Then you run a piece of code, and you try to have a formal implication that the preconditions with the code imply a postcondition. Which again is some statement about the variables and the output. For most types of programs, this is relatively easy to do. If you just have an assignment of a variable, for example, then the precondition has something to say, and then the postcondition is there's a new variable and it has the value that you assigned it to. And similar for if statements, these are all relatively easy to handle. The only interesting part is when you have a while loop. Because then again, the same code might run many times, and it's not so clear what its effect is. So there's a template for handling that. You have some precondition before the loop, and you try to prove some postcondition after running the loop. And the template says that's not enough. You also have to come up with what's called a loop invariant. That's a specific statement. And it has to satisfy three conditions. Namely, it should be true before the loop. So I has to be true here. Then if you have the invariant and the condition that means you continue another iteration of the while loop, then the invariant has to be reestablished at the end of the loop. And finally, if you have the invariant after the loop, then together with the statement that the while loop does not continue must give you the postcondition you wanted. Okay? Let's see a concrete example for this one, and maybe that becomes a bit clearer. The example is this piece of code. It's a simple function that computes the maximum entry in an array of numbers. I'm sure most of you would be give you 5 minutes and you coded this up in some language. So how would you find the maximum in an array of numbers? Well, you go through, you keep a running maximum from the beginning in this case. So we have a variable I that goes through the array from starting at 1 and until the end. So I should maybe point out my arrays start at 0. That's the default. And I use these square brackets to index elements like in almost all languages. And here this function has a precondition, namely that n is at least 1. You're not allowed to call the function with an empty array. I guess it makes sense because it's hard in general to return the maximal element of an empty set. It's not well defined. If it's numbers, maybe you can find some infinity value, but let's ignore that. So we have a precondition, which is this one in this case. That's something the program can rely on when you run it, and your proof can assume that. Then how do you find the maximum? You keep a current maximum that's starting with the first element, and then when you iterate through the array, if the new element is bigger, then that's the new running maximum, and otherwise you keep the old one, right? So the code is not very interesting or not very complicated, but how can we formally prove that this does the right thing? So clearly, the post condition should be the output, what I return here, current max at the end, should be the maximum element in this array. That's the post condition we want. And that's spelled out here in formulas. So at this point, at the line 13, or after line 13, I want the current maximum variable, current max, to be the largest element in the array. And well, I hope that's readable for you, even if you haven't seen that before. It just means let k run in this range and then pick the largest value that you get on the right. Okay, so how do we prove this? The tricky bit is to find a loop invariant. And I've already done that tricky step for you here. So I'll just show you how the final proof works. This will not really teach you how to find these proofs, but I mostly want you to be able to read them and understand and recognize if they're correct. Okay, the loop invariant is often something you don't find in the first round, but you have to refine, and that's the part I've already done for you. There are these two bits. The first one talks about current max, as you would expect, and the second one talks about this I. And we'll see where this gets used. Do I have well, I also use this in the template condition. That's the condition of the while loop. So that's what is just copied here. To follow the template, remember we have to do these three things. We have to check that the invariant holds before the loop, that together with the condition of the while loop, it implies that the invariant is re-established after the loop, and that it gives us the desired post condition at the end. These are these three things that we have to prove. And so let's go through these one by one. Why does the loop invariant hold at the beginning, before the loop? Well, let's look at the two parts. There's the red and the green part. The red part at this point, the important bit here is that I is 1, because it was just assigned to 1. So current max at this point is just assigned to A0. Now, if I look at the loop invariant and I insert what I is, namely 1, then that's the same as this complicated looking term. But if k is just in the range from 0 to 0, that's really all I'm just saying is it's A0. So that's the red part. The red part of the loop invariant is satisfied at this point, just because it doesn't actually make an interesting statement. It just says current max is A0. Okay? And for the green part, we assume that n is at least 1. So if I turn that around, it means 1 is at least n, and that means I is at most n. Sorry, 1 is at most n, and that means I is at most n, and that's what the loop invariant here says. Okay, so I've proven both parts of the loop invariant of this AND statement are true at position A in the code. And that was the first part of the template that we had to do. All right? The more tricky bit is part 2. That's inside the loop where actually something happens. So I tried to keep this here on the slide. Maybe it's a bit small. So we have an implication that we have to prove. And in this case, we can basically do a direct proof, but we'll use a case distinction. Because in the loop body, there's this if statement, so it makes sense to make a case distinction based on that one. And it's basically the condition of the if, so and I guess I should be precise and say in that specific line, because variables keep changing their values. Now there's two cases that can either be true or false, this if condition. So case A, or let me spell it out. Case A is that is true. So AI is bigger than the current max. That means we have found a new maximum, right? Let me copy it. Okay, so that's all we know so far. But now we have to use the fact that the invariant is true. Remember, we're allowed to use, in this case, we're doing a direct proof. So we assume what's on the left of the implication and try to prove what's on the right. In particular, that means we can use our loop invariant. And from the red part of the loop invariant, we can use this bit. Now in this case, I has some value that we don't know, so we'll have to leave it symbolic. That's from I, the loop invariant. And now I'm just copying what's on the previous slide. So k between 0 and I minus 1. All right, now we have to use that we know what the if statement will do. Because we're in the true case, we will execute this line 9 and update current max. So in this line, we change the value of current max. Namely, we set it to AI. Right? And that means current max now is AI, but that is nothing but the maximum up to the next position, because we know from this part that the last entry is the largest, so I can go from k between 0 and including I. And I know the maximum will actually be the last element, which is AI. All right. So far so good, but this is not what the invariant says. The invariant should have the I minus 1 again, so this doesn't seem like we make progress. But then if you look at the next line in code, we are now changing the value of I. And so after that, now I'm sick and tired of writing this all the time. Let me just copy it. Now current max is still the same, but I've updated I. So if I want that to be the same, I have to do the I minus 1 again, right? I've just taken this term and replaced I by I plus 1. So I have to do the inverse in here. Well, and that is the red part of our invariant down here. That's the red part of the loop invariant reestablished. In this case. We're still in case A. Okay, I'll try to get the indentation right. Case B is the false case, which means now I should be able to copy some bits. If it's not greater, then it's less or equal. And current max by the loop invariant still is this, so almost a bit, it's almost indicating we're doing too much copying. So that's still true because it only uses the loop invariant. But now, because AI is smaller than this maximum in the previous range, I know this is actually the same. So that uses this condition. Maybe I should also do it in blue again. That means that's actually the same than letting k go one further. Now, in both cases, we arrived at this statement that current max is the max of the positions up to including I. but for different reasons, right? In one case, we had to do the if and update it. In the other case, we did not update it, but it was still the maximum. And then the rest is the same. So after line 10, we again change I. We update I. So I'll do the same changes here. And so again, the red part of the loop invariant is reestablished at D. Good. So that's almost done, but we also need the green part of the loop invariant. We also have to show that this is still true. And that's maybe not trivial because we change I, right? So to prove this, we use that I really want the code again. I used too much space, so I'll shrink it a bit more. Hope it's still somewhat legible. So at position B, the loop invariant was true, and so the green part of the loop invariant says I is strictly less than n. The only place where we change it is again at line 10. Let me use the assignment. And if I was less than 10, strictly less than 10 before, now if I make it one bigger, it's still less or equal n. And that's what the loop invariant wanted. So also the green part is true. And note that for the green part, we didn't have to do the case distinction. The if doesn't change the outcome there. Now that means we've proven the second part of the statement. And it's a while ago, but we've established this one now. If the loop invariant holds at the beginning of the loop, together with the loop condition, it holds at the end of the loop body. Now what's missing is the last part, namely that we're proving the right thing. And this one will be short, I promise. Can I copy this part? I'd have to take a... I can take screenshots. Let's do it that way. And what we're trying to prove is this. And let's also be lazy and copy the post condition. So that's my service to you. You don't have to remember everything. It's all on the slides. Put it all on the side. So we take our loop invariant and add the condition of the while loop, negate it. That condition was that. So if I take I and negate the condition, what I get is the loop invariant, and the negation of that is I greater equal n. Now if you look at the green part of the invariant, that means I should be less than n and greater, less or equal n and greater equal n, so I is equal to n, right? And now I take the red part of the loop invariant and insert I, the value of I. And so it says current max is the max for k in the whole range. And ta-da, that's what the post condition was. Okay, so that concludes the third part. We can tick it off here. We've proven that if we have the loop condition after the loop, plus the negation of the while condition, so that we actually terminate it, those two things together imply what we wanted, namely current max is the maximum of the entire array. Oof, yeah, I know, it's tedious, right? This is the level of detail that you need for formal verification. That's the level of detail that a computer can follow a proof and check step by step that it's correct. I would have to spell it out in a different language. I've used English language to convince you, and you can formulate it in a logic language for a computer. But that's the kind of level of detail where no further doubt is possible. We'll often stop a little higher level than that with a bit more abstractions in. But I want you to be able to recognize when a proof is formal and at least be able to read them. You'll do another two basic examples of that form in the tutorials, namely on mathematical induction and on the termination proof. And hopefully then you have at least a feeling for what these proofs should look like. That's all for this unit. If you want, we can go through a few Slido questions. But if you have to run for another lecture, that's also fine by me. And I'll see you next Thursday or on Campus Wire.
Do we need to move all this proof?
Let me stop the recording before we... It looks like we're not doing the Slido questions. So stop the recording first.